All right, let's get started with Chapter 4.1, the very beginning of Chapter 4, radian and degree measure. So, just to get started, let's talk about angles, going back to your geometry days. All right, so every angle has three important pieces to it. You have your initial side, and then we rotate through some angle to get to the terminal side, and the point we're rotating about is the vertex. So in this chapter, we're going to work in standard position most of the time. And what standard position means is that our initial side is the positive x-axis, the vertex is the origin, and then when we rotate, wherever we stop, that becomes our terminal side. If we rotate counterclockwise from quadrant 1 to quadrant 2 to quadrant 3, that direction, that's going to be a positive angle. And if we go the other direction into quadrant 4, we're going to call those angles negative if we're going clockwise. Alright, so we can have what are called coterminal angles. Angle alpha and angle beta are coterminal angles in that they result in the same terminal side from the same initial side, but they rotated through different angles. A went through a positive spin, alpha went through a positive spin, and beta went through a negative spin here. Notice how you could have two positive coterminal angles. Angle beta spins around 360 degrees and then again a little bit more to match up with alpha. So coterminal angles just mean the same ending point, but maybe we have a different number for our angle, positive, negative, or we spin around more than 360. Alright, so now let's talk about a radian. So a radian is a new kind of measurement that matches up with degrees. Just kind of like with you have temperature, you have Celsius and you have Fahrenheit. So in degrees you have, in angles you have degrees and you have radians. And what a radian is, one of them, if we had some arc, if the radius here was the same amount, if we picked it up and stretched it over the circle, if that was the same amount, that distance of rotation is one radian, okay? And the symbol we use for radians is theta. So theta equals S, which is the arc length, all right? From here, all the way around to here, we're going to call that S. And if that's equal to R, the radius, then we have 1 radian. And the radians are always the arc length divided by the radius. That's how we're going to find it out. Alright, so if we look in here, we've got some set things. When we spin around, there's some important spots on our rotation. So we don't really typically use just regular numbers, 1, 2, 3, 4, 5, 6, because they don't match up with 360 degrees. We're going to use pi, and this is where pi comes into place a lot. Pi over 3 goes around 6 times. Pi over 6 will spin around and land evenly. Pi over 4 will land evenly because they all line up with, these are the important ones. Pi over 2 is 90 degrees. Pi itself is 180 degrees. And 2 pi is a full circle. 2 pi is 360 degrees. Okay? Alright, so we have this phrase, the terminal side of theta lies in a quadrant, is often abbreviated by simply saying theta lies in a quadrant. That means that if our angle is like this, and our terminal side is in quadrant 1, okay, then we're just going to say the whole angle is in quadrant 1. If our terminal side ends up over here, then we're going to say the whole angle is in quadrant 3. Alright, so for the positive angle, 13 pi over 6, subtract 2 pi to obtain a coterminal angle. Alright, so we're doing coterminal angles. You've got the steps here, but if we wanted to make it step by step, 2 pi is, if we made a common denominator, 12 pi over 6, so we end up with pi over 6. For B, for the positive angle, 3 pi over 4, subtract 2 pi to obtain a coterminal angle. So 3 pi over 4 minus, we need a common denominator, so it's going to be 8 pi over 4. We'd end up with negative 5 pi over 4. And we could also do a negative angle and add 2 pi to obtain a coterminal angle. 12 we can make as 6 pi over 3 to get a common denominator. Negative 2 plus 6, positive 4. All right, so see if you can come up with the coterminal angles for these, A and B on 27. All right, now let's talk about complementary and supplementary. If you think back to algebra, complementary means we add up to 90 degrees, supplementary to 180. Okay, but if we're dealing with radians, then complementary means we add up to pi over 2 is the same thing as 90, and 180 degrees is the same thing as just pi. So if we want to say what's the complement of 2 pi over 5, we would say, okay, let's start with 90 degrees, but in radians. So pi over 2, subtract the 2 pi over 5. To do that, we need common denominators, and if you do it right, we get pi over 10. All right? So you can see there's another example there for the supplement, but let's look at B. 4 pi over 5, we want to find the supplement and the complement of that. Okay? For the complement, there is no complement because 4 pi over 5 is over here. Okay? It's bigger than 90 degrees. So you can't have a complement with something that's bigger than 90 degrees. But you could have a supplement. So we can do our supplement of pi minus 4 pi over 5 and end up with 1 pi over 5. All right? What if we had an angle bigger than 180? Then we wouldn't have a complement or a supplement for that angle. Go ahead and see if you can find, if possible, the complement and supplements of those two angles for A and B. All right, so now we'll look at the thing we are more familiar with, degree measures. So these are the important numbers on our, we're going to call this the unit circle. And a unit circle is a circle where the radius is 1. So 1 unit, right? We don't have centimeters or meters or feet, just 1 unit. So we'll call it the unit circle. And so we go 0, 30, 45, 60, and 90 are the important numbers. And you'll notice how those numbers just keep spinning around if we go into the other quadrant. So 90 plus 30 plus 45 plus 60, and then another 90 degrees. 180 plus 30 plus 45 plus 60, and so forth all the way around. So these are the important numbers. Are going to come up a lot. Let's see how we switch from degrees to radians. And here is our divider. So we need to find 1 degree that matches up with a radian measure. 180 degrees matches up with pi. All right. We could say 2 pi over 360 if we wanted to. We could say pi over 2 over 90 if we wanted to. But pi over 180 is kind of the easiest fraction to work with. All right. So the conversion, 1 pi equals 180. And let's go ahead and see how we would do this. We want to turn 135 into radians. So degrees is on top. We want to cancel degrees out. So in our fraction, we make sure it's radians over degrees. So the unit of degrees cancels. 135 over 180 is 3/4 if you reduce. So we have 3 pi over 4 radians. All right. If we wanted to go the other way from 3 pi over 4 to degrees, we would still multiply by this, but flipped over. So radians was on the bottom, so we would cancel. I think you can do it. See if you can turn 30 and 45 into radian measures. All right, and so example 4 is going the other way. We just talked about that. If we want to go radians to degrees, use the same fraction with radians on the bottom. So I'm not going to go through all 3 of these. I think you can do it. See if you can do problem 61. Turn those radians into degrees. All right, so now that we have that, we're going to try to do some applications with them. Okay. So the first thing that we want to be able to do is find the arc length. So if we know a radius and we know the angle, how long about the circle are we going to be traveling? So let's try an example, see if it makes sense based on the example. We do have a formula here, S equals R theta, and this comes from our original formula, theta equals S over R. We just multiplied both sides by R. All right, a circle has a radius of 4. Find the length of the arc intercepted by a central angle of 240 degrees. So 240 degrees is a pretty large angle. Spin it all the way around here. So our central angle is 240. And we want to know S from here all the way over to here. And 240 is more than 180. Let me draw this correctly. 240 would actually be this angle, because it's more than 180 degrees, more than the straight line. We know the radius is 4. Let's find S. All right, so S equals R theta. So we're just going to say S equals R theta, not degrees. So that's the mistake people make. We can't just use 240. We have to turn this into radians. So we have to go pi over 180 degrees. Degrees will cancel. 24 over 18. Let's reduce it down. We can divide those both by 6. So 4 over 3. There we go. So we've got equals 4 times 4/3 pi. So we're going to get 16 pi over 3 would be our arc length, which is the distance around the circle. All right? Same exact steps. See if you can do problem 89. All right, now we're going to get into linear and angular speeds. All right, so linear speed is the thing we've always dealt with our whole lives, how long it takes us to go in a straight line. Okay? For angular speeds, that's how fast we're spinning in a circle. Okay? So if we start with a circle, think about a bike. We have a bike wheel. All right? And we take this bike, and we want to know how far we've traveled. Well, if we were a spot on this circle, and we were traveling around in a circle, that's the distance that we've traveled. So we could take that circle and unwrap it, take it from right here, and lie it in a straight line on the ground. We can figure out how much distance we've traveled. And so that's this formula. Take the amount of circle length you've gone around, and then divide that by time, right, to get speed, because speed is going to be distance over time. All right? We also need to figure out the angular speed, how many angles we traveled through, how fast we're spinning around in one place. So that's how many angles we go through in radians, and divide that by time. Okay? And that's going to be omega. The W here is omega. All right? So we've got these two formulas, S over T and omega over T. I'm sorry, theta over T equals omega. We'll clean these up. These will become more familiar as we go through them. All right, so we've got these three formulas that we want to memorize. All right, so V equals R from up here. V equals ST. We've skipped to some steps to get to this one. Let's figure out how we get R omega for V, which is our linear speed. Okay, so we know that S equals R theta, right? S over T, which is the same thing as V, right? Your straight line speed equals R theta over T, and theta over T equals omega. So we can substitute these things in here for omega. A couple different formulas. You're going to want to have those down in your notes. Pause this if you need to, but I'm going to move on and do example 6. The second hand of a clock is 10.2 centimeters long. Find the speed of the tip of the second hand as it spins around. All right, so we know that. Let me spin back so we have our formulas. V equals R. I'm going to use this one. R theta over T. R theta over T is our V. And the reason I picked that formula is because those are the pieces of information I know. I know that my radius is 10.2 centimeters. We want to keep our units for these problems. Okay, the linear speed as it passes around the clock face. All right, well, how many radians do I travel as I spin all the way around the clock face? I go in a full circle. So I know that I'm going to go 2 pi. How long does it take me to go all the way around this? Well, the second hand of a clock, the second hand takes how long? It takes 60 seconds to travel all the way around a clock face. All right, so if we multiply those things together, we're going to have 20.4 pi centimeters over 60 seconds. Right, and so let's grab the calculator and do some quick division. And so 20.4 divided by 60 equals 0.34, and we keep the pi here. So 0.34 pi centimeters per second. So we could multiply by pi if we wanted to get that out of there. A lot of times in these problems we're going to leave in pi. See if you can do 111. Same formulas here for 111. All right, 2 more examples to go with these. The blades of a wind turbine are 116 feet long. The propeller rotates at 15 revolutions per minute. Find the angular speed of the propeller. All right, so angular speed, omega, is theta over t, okay, in radians per minute. How many radians does it go through? 15 revolutions means 15 circles. How many radians in a circle? 2 pi. So 15 revolutions means 15 times 2 pi. Now what's our time? Time is 1 minute. So here we have 30 pi radians per minute would be our units. Okay, so that's A. Let's find B, the linear speed. V equals R omega. So on this one, we already have omega. We just need to throw in R, which is 116 feet, times 30 pi radians per minute. All right, and when we do this calculation, we're not going to usually include the radians because we're assuming that it's the circle has been flattened out into a straight line, so we no longer have radians. So now it's just 116 over 30. Let's punch that in. 3.86 repeating. 3.867 feet per minute would be our answer on B. Try 113. All right, last thing we've got here, we've got a formula for the area. Remember, your old formula for the area of a circle is pi r squared. Okay. Our new formula is the exact same thing. We still have r squared, but look at the new part is 1/2 theta. Theta is how much of the circle we actually go around. If we go around a whole circle, we'd have 1/2. A whole circle is 2 pi. Look what happens to the 2's. They cancel out, and that's where the pi comes from. So this formula you've had your whole life has actually been this formula, just simplified, assuming it's a whole circle. Okay? But we don't have to figure out a whole circle. We can just figure out the area of parts of a circle. So here we go. Sprinkle on a golf course, sprays water over a distance of 70 feet and over 120 degrees. So all these formulas are in radians. So first things first, let's change that into radians. 2 pi over 360. Oops, I went the hard way. Pi over 180 is easier than 2 pi over 360. Either one would have worked. All right, so 12 over 18 is 2/3. So we've got 2/3 pi equals our theta. Our r is 70. So our area is going to be 1/2 r squared theta. So 1/2 70 squared times 2 over 3 pi. And we want this to the nearest, doesn't say, so we'll probably just do 2 decimal places. Let's go to the calculator. 1/2 times 70 squared times 2/3 pi. 5,131 feet and 26, well, can't go into inches because we'd have to do the conversion. So 0.268 feet is what we would have. Finish up with 117 and you are done. If you have any questions, we will go over this in class. Good luck.